We want to talk more about agentic negentropic dynamics from a different perspective, and we just want to talk about it as a physical theory of intelligent agents. So again, as you may know already, our project here is to take a look at physics and biology and biological intelligence, basically. And in this framework, an intelligent agent is fundamentally a system that must do three things. It must maintain and update beliefs about what's happening in the world. It also has to make decisions about what actions it's going to take in the present. And of course, it has to store information from past experience so that it can do better in the future. So the AND framework, Agentic Negentropic Dynamics framework, it begins from the recognition that all of this is happening within a single physical body or physical device that's operating under fixed thermodynamic constraints. Now, just as a human brain consumes energy and can't exceed certain limits of computation or limits of storage, so too an artificial agent has finite processing power. It also has finite memory. It also has finite energy budgets. And these are not incidental limitations. These are not just things we impose because we want to experiment. No. They're not outside elements. They are fundamental to how the system must be designed and how the system must behave, because we want, again, biologically inspired, efficient intelligence, not the sloppy, wasteful intelligence that we find with legacy deep learning and old school machine learning. So we really have to start thinking about thermodynamics from a different perspective here, much more seriously. So the agent, as we've defined it, exists in a state space, a virtual state space that can be divided into different kinds of variables. And each variable would operate in its own time scale. Let's think about driving a car, for example, on a highway. Now, you as an agent, a car driving agent, your reflexive actions like steering, like accelerating, like using the brakes, these are reflexive actions. They happen in the moment and they respond almost instantly to inputs from your eyes and ears. These are the fast variables. Remember, they're operating at their own time scale. Now, at the same time, your route planning, your mental map of the highway systems or the road systems, you even are aware of your fuel consumption. They're changing much more slowly over the course of your trip. These are your slow variables. Your current uncertainty about road conditions ahead, your confidence in different possible routes, all of these are slower. They're your beliefs. And then remember, you have your memory of previous trips that you've made throughout your life. I mean, you may have learned patterns about traffic at different times of day, for example. And these are all going to form a memory subsystem. They could be thought of as priors, deeper, slower priors, like adiabatic, slow-changing priors. But anyway, agentic negentropic dynamics, it treats all of these variables, all of these different time scales, as interacting parts of just one single mathematical object. It's a product manifold, which it's just simply a space that naturally factors into distinct but coupled subsystems. Now, the dynamics that govern how all these variables evolve, they're built on a principle called metaplectic structure. Metaplectic structure is a way of organizing physics which naturally incorporates two fundamental types of behavior. There are conservative dynamics and there are dissipative dynamics. So think first law, conservation of energy, and second law, dissipation of order, entropy. The first type of dynamics, of course, like we mentioned, is conservative dynamics, and this just means energy is neither created nor destroyed in this system as it evolves. And you can illustrate that by just thinking about a gyroscope. So you have a gyroscope spinning in a vacuum, and what does it do? It keeps spinning indefinitely because nothing removes its rotational energy, so it's conservation of energy. There's no change. So conservative dynamics in this framework are generated by what we call skew operators. Skew operators are just mathematical objects with a special symmetry. Again, we're going to talk about symmetries later too, so if you don't understand those, don't worry. But anyway, these skew operators have these special symmetry properties, and the result of them is that they guarantee energy conservation automatically. So again, conservative dynamics. The second type of behavior is dissipative dynamics. And this just means that energy is being consumed or it's being converted into heat, waste heat. So when a spinning gyroscope, the one we were talking about before, let's say we let air, it's no longer in a vacuum, we let it to experience air resistance. When we do that, it gradually slows down. So that's dissipative dynamics, and these are generated by what we call positive semi-definite operators. Now these are just mathematical tools which measure how strongly different variables are dragged down towards some equilibrium state. Now, in any real intelligent agent, both of these things are always happening together. They are obeying thermodynamic laws. So the fast reflexive subsystem, for example, is conserving energy as it computes motor commands in responses to your sensory inputs. But this fast computation happens within the context of a slow subsystem that consumes metabolic energy. It's losing heat. It's gradually adjusting its inner parameters based on its experience. And so that could be thought of as a dissipative layer. And that metaplectic substructure, it mathematically couples these two types of dynamics so that they coexist in this single coherent description, in this single state space. So we're not using this as a metaphor. This is not just some kind of loose analogy. There are, again, mathematics, the skew, and positive semi-definite operators. There's mathematics to guarantee, even as the agent processes information and makes decisions, that it will automatically obey the second law of thermodynamics, which states that disorder in the universe is going to increase or stay the same, but it never decreases. Now, the agent can reduce the disorder in its own internal states. Like, it can become more certain of something, or it can become more organized in its internal logic. But it can only do this by, number one, consuming energy, and number two, by producing heat in the environment. So the total increase in disorder is always going to be positive. Now, the entire behavior of the agent is derived from a variational principle. A variational principle is just a mathematical idea that actually it's proven extraordinarily powerful in physics. How it works is you don't just write out equations that say how the system changes at each instant, like step by step. What a variational principle is that you write down a single quantity, which is called an action. And that quantity measures the total cost accumulated over the entire trajectory of the system through time. Now, the equations of motion they emerge from requiring that this total action must be minimized. So think, for instance, of light. Light travels through a medium along a path that takes the least time. So it's a least action principle. Think of Fermat's principle. But electrons and photons, they're following trajectories that minimize an action, combining kinetic energy and potential energy and interaction effects. So again, this is the principle of least action, which is really a different manifestation of Newton's second law, a different manifestation of the Hamiltonian. It's a different manifestation even of Schrodinger's equation. But anyway, the A&D framework, it applies the same principle, the same least action principle, to intelligent agents, basically. So this is this variational principle. Now, the action being minimized, it accumulates three distinct costs. The first cost is the physical Lagrangian, and that should be familiar from classical mechanics. It just measures kinetic energy minus potential energy for the fast subsystem, and that represents the mechanical work being done by the agent's body as it moves and acts. Now, the second distinct cost is the free energy, if you're familiar with first and free energy. This combines the expected cost of the agent's actions, like how well its decisions align with its goals or rewards on one hand. It combines those costs with an information theoretic penalty. This penalty is proportional to how much the agent's current belief differ from prior knowledge. So in other words, the agent pays a cost not just for getting things wrong, but also for being surprised relative to what it already believed. So it's like an error penalty. The higher the error, the more penalty it pays in energy. So then the third component, the third cost component here is the dissipation cost. And that is going to account for the thermodynamic work that's required for the agent to actually implement its computations, for it to update its beliefs, for it to modify its memories, and also, of course, moving energy around in its substrate is also a cost that's covered under this dissipation cost. Now, all of this is subject to constraints, of course, and so the trajectory has to obey that metaplectic master equation. The total metabolic energy consumed, it can't exceed the available budget, of course. And the internal representation of the world, it has to respect the symmetries of the environment. If the world looks the same after a rotation, the agent should not have to waste capacity by learning that rotations matter. It should already know. I mean, when you minimize the total action subject to these constraints, the mathematical stationarity condition, it's going to yield a system of equations that govern how beliefs evolve. It's going to govern how fast variables oscillate, how the slow variables drift, how memory updates accumulate, and how the agent allocates its finite energy budget across all of these competing demands. So it is deterministic and optimal in the sense that the small perturbations in the trajectory, they would increase the total cost. And one of the most important constraints built into this system is the Landauer accounting. The Landauer principle states a simple but profound fact. Erasing information is a thermodynamic operation which requires a minimum amount of work. So that when you have a bit of data in your computer and you overwrite that, then the operation must, at minimum, release a certain amount of heat in the environment. Now, if it's just a bit, yes, it's a tiny amount of heat, but when you have a hyper-intelligent system, that heat adds up. The amount of energy actually depends on the amount of information erased and also the absolute temperature. So in the context of belief updating, Landauer's principle has direct interpretation. When the agent's belief, when it becomes more certain, when it narrows the probability distribution from being spread over many possibilities to being concentrated on just a few possibilities, well, what just happened? Possibilities have been erased, right? So this literally destroys information about alternative states, and this erasure of possibilities, it carries a thermodynamic cost. Now, the agent models this cost through a quantity that we call erasure proxy. And this is simply the logarithm of how much the agent's uncertainty decreased. I mean, if the agent started with a covariance matrix, would be a mathematical description of uncertainty. So they start with a covariance matrix, and after gathering some evidence, the agent ends up with a smaller covariance matrix, the ratio of their determinants, like taking the logarithm. This gives a proxy of how much information was erased. And the actual thermodynamic cost is this proxy multiplied by the Boltzmann constant times the absolute temperature. So it's not really that complicated. But when the agent is about to update its belief, it first computes how much energy this update would cost by calculating that erasure policy. And if the update would cost more than the remaining metabolic budget, then the system has a problem. It can't afford to become certain, really. So it either has to accept some kind of less dramatic update that costs less energy, or it might have to reject the update entirely and then continue with its previous beliefs. But anyway, this creates a very hard constraint. We need to be strict about our energy budget. Beliefs cannot improve arbitrarily. They only improve to the extent that the agent has the energy to spend on becoming less uncertain. Well, this is one way that biological intelligence is so parsimonious. It just obeys the thermodynamic energy budget. You might think that this is an odd constraint to impose on a learning system, but it is real. It does capture something very real. Think of an animal that might be tired or hungry. That animal might have depleted energy. And what does it do? Well, if it does not have the energy reserves, it can't afford to perform any kind of complex deliberations. And what's it going to do? It's going to have to rely on rough heuristics. It's going to have to rely on habitual behavior, maybe instinct. And it won't be doing any precise calculations because it doesn't have the energy to do so. Likewise, a cyber agency like a robot running low on its battery, it's going to have to conserve its computational powers. An algorithm operating under strict real-time constraints, it can't afford to refine every decision to high precision. That's the point. So by incorporating Landauer's accounting, then agentic negentropic dynamics captures these trade-offs naturally. And what we're seeing emerging here is that we're not so concerned about the tiny amount of energy that's being, burned when a bit is erased. What we're concerned with is the underlying lessons that are taught by the parsimony of biological agency as it respects these thermodynamic budgets. Now, the agent has another strategy. It actually exploits structure. We've mentioned this before. It exploits structure in its environment through symmetry. So this is energy conservation strategy. Let's discuss this. Because most environments, they do contain transformations that preserve the essential structure of whatever the problem is. So like, let's say you're navigating your car in a parking lot. Now, if you rotate your navigation problem by 90 degrees, that doesn't really fundamentally change the problem, right? The road layout is the same, it's just been reoriented. So, if you're sorting identical objects, then the order in which you sort them does not matter. They're identical, right? Permuting them produces an equivalent task. So rather than learning independent representations for every possible rotation and every possible permutation, what would an intelligent system do? Well, it should learn the functions that behave predictably under these transformations. A function is equivariant if it transforms in a predictable way under symmetry operations. Rotating the input produces a rotated output. A function is invariant if the symmetry operations leave it unchanged. So you have both equivariant and invariance, and if you have the correct functions built in already, then you have a prior that saves you energy. And the A&D framework incorporates this through symmetry quotienting. Symmetry quotienting constructs a reduced representation space where symmetrically equivalent states are treated as genuinely identical instead of just merely equivalent. If you quotient out your rotation symmetry from a navigation space, you reduce the dimensionality because you don't have to like separately encode every rotated version of the same configuration anymore. The exact projector implements this by averaging a learned representation over all members of the symmetry group. So if there are 8 rotational symmetries, you evaluate the same representation function on all 8 rotations of the input and then you just average the result. And what that does is it just ensures that the representation automatically becomes invariant to rotation. And such symmetry respecting learning, again, it just drastically reduces the amount of data, the amount of computation that you need, because the agent isn't wasting capacity learning that rotations are equivalent. Instead, the architecture itself ensures they're treated as equivalent from the start. Now, to make predictions about future states without simulating the entire nonlinear dynamics, this is a big problem. You have nonlinear dynamics. Well, how do you do that? Well, the agent is going to use Koopman operator theory combined with online learning called recursive least squares. Now, the Koopman idea is very elegant, actually. Given a nonlinear dynamical system, you can lift it to a higher dimensional space of observables where the evolution becomes approximately linear. So imagine a pendulum swinging with a complex amplitude-dependent oscillation. So in this original position velocity space, the dynamics are nonlinear in that system. It's going to be difficult to model. But if you lift to a space of observables like sine of position, cosine of position, and several trigonometric combinations, then that same pendulum motion becomes approximately a linear rotation in this higher dimensional space. The benefit is enormous. Linear systems are far easier to predict than nonlinear systems are. So you can just solve them explicitly. You can compute their stability, and you can simply forecast their behavior with basic matrix multiplications. So the Koopman operator is a linear operator in this lifted space that advances the observables forward by one step at a time. And then the RLS algorithm, the recursively squares algorithm, this learns the operator incrementally by accumulating 2 matrices. Okay, one of the matrices tracking the outer products of the observables at each time point, and that's the M matrix. And then the other matrix is going to be tracking the outer products between present and future observables, and that's the Y matrix. And so at each step, with a small forgetting factor in as well, old data gradually becomes less important and new data begins to dominate. And so to make a prediction, then the agent just computes the linear predictor as Y times the inverse of M. And then it applies it to the lifted features of the current state to forecast the next lifted features, finally transforming back to observable variables again. Now this produces an online learnable predictive model that requires no matrix inversions, no decompositions at each update, and only accumulation and one inversion per prediction. So really, Koopman operator together with RLS is really an advanced tool in the toolbox here. The predictive operator feeds into the fast dynamics as a forcing term. And by predicting where the world will be in the next few time steps, the agent can then preload appropriate responses early, right? So this is how a tennis player might begin moving before the ball reaches them. The tennis player's fast subsystem, it receives these forcing signals from slower prediction mechanisms that have already computed roughly where the ball is going to arrive based on the ball's early trajectory. So what happens here then is the agent becomes proactive instead of purely reactive, and that is powerful. Now, memory formation in the agent is going to follow the Hebbian plasticity. This is the principle obviously named after Donald Hebb. The famous phrase that neurons that fire together wire together. In the mathematical model, this means that when two variables are simultaneously active, then the connection between them is going to be strengthened. And the implementation uses the outer product updates to a weight matrix, where you take the outer product of the presynaptic activity, like an input signal, and the postsynaptic activity, a learned signal or a response, and you add it to the weight matrix with some learning rate. So over time, frequently co-occurring patterns strengthen their mutual connections, and that creates learned associations. So it identifies and preserves patterns. A problem, though, is that without regulation, Hebbian learning would lead to unbounded growth, right? I mean, if you keep applying outer product updates, the matrix norm keeps growing. It just keeps growing and growing. So in the brain, there are various homeostatic mechanisms that prevent this from happening. So in agentic negotropic dynamics, we have a spectral proximal repair mechanism, and it enforces an upper bound on the spectral norm, the size of the singular value of the weight matrix. There's a bound placed on the weight matrix. This is done by computing the single value, by computing the SVD, and then we clamp down the largest singular values to a maximum threshold and then reconstruct. Additionally, you might have very weak connections, so those have to be sparsified away. We just have to prune them or remove links that fall below a significant threshold. And this, in turn, creates a memory subsystem that grows and strengthens with use, but also that remains thermodynamically bounded, and it remains computationally tractable. The discrete implementation of these coupled systems uses a structure-preserving operator splitting. What this means is that at each clock tick, the system executes 3 sequential sub-steps. First comes the symplectic Hamiltonian step. This is a type of geometric integrator that's specifically designed for conservative dynamics. And then the symplectic property, what that means is that the integrator preserves the volume in phase space, and more importantly, it does not artificially create or destroy energy over long simulations. So even if you run the integrator for millions of steps, the total mechanical energy of the fast subsystem is just always remains stable. And of course, this is going to be crucial for reliability. I mean, a non-symplectic integrator would gradually accumulate numerical energy errors that would corrupt its predictions over time. So that's why you see symplectic integrators being widely used in astrophysics, because you need to track a planetary motion over billions of years. So without the symplectic integrators, you would just accumulate numerical errors until you wouldn't be able to rely on any kind of long-term forecast at all. They'd just be meaningless. Okay, well, second, you have to have a proximal dissipative step that updates the belief state. And this solves a constrained optimization problem that minimizes prediction error against observations while at the same time regularizing how far the beliefs are allowed to jump, weighted by the Landauer cost. So the proximal algorithm handles both the objective and the constraint efficiently, and then it can incorporate the metabolic budget's hard limit, such that if the proposed update would exceed the energy budget, the algorithm scales it back or it rejects it entirely. Okay, third now comes a Hebbian increment that adjusts memory weights based on current activity patterns. This happens at the same regular time interval as the other updates, and it creates a unified stepping system that respects each subsystem's mathematical structure while maintaining overall coherence at the same time. Now, so when the full state space becomes too large to simulate in real time, the subsystem has to compress its internal model through model reduction. So the theory of Gramians provides a principled approach to doing that. The controllability Gramian measures which dimensions of state space can actually be influenced by the agent's inputs and actions, and then the observability Gramian measures which dimensions actually affect the outputs that are observed. So if a dimension of state space is either not controllable or not observable, then it can't be part of any input-output relationship, and the agent might as well just ignore it. So Gramians come in handy here. The product of these two Gramians yields a quantity that's called the Hankel singular value for each state dimension. These rank order the dimensions by their importance for input-output behavior. So a dimension with a large Hankel singular value contributes significantly to relating inputs to outputs, but a dimension with a tiny value is pretty much unimportant, it's irrelevant. So you can truncate away the least important dimensions. You can keep only the top top-ranked dimensions, and then you get a reduced order model. The error introduced by this truncation can be bounded mathematically. You can prove that the difference between the full and the reduced models applied to any bounded input signal will not exceed a certain threshold. You can obviously do that, and this is going to allow intelligent simplification of internal models. But identifying these reduced models, it's going to require finding that low-rank operator that fits observed trajectories, but it also has to respect the metroplectic structure. So there, empirical dynamic mode decomposition, or EDMD, will solve a least squares fitting problem where you minimize the distance between predicted and observed dynamics. But simply minimizing error, of course, is not going to be enough, because the solution also has to decompose into a skew Hamiltonian part. That's the conservative part. And then a posterior semi-definite dissipative part. And this is enforced through alternating projections. You compute the least square solution, and then you compute the skew symmetric part to be exactly skew, and project its symmetric part to be positive semi-definite, and repeat until you get some convergence. And this is going to ensure that the learned model remains physically realizable, and also it has to be thermodynamically consistent at the same time. Now, for very large data sets, of course, computing the full singular value decomposition is going to become, just impractical. It's going to take too long and be too intensive. So we use RSVD, or randomized weighted SVD. And then you use random sampling to approximate the decomposition without explicitly computing all the singular values. The algorithm sketches the data matrix by multiplying it with just that random test matrix, which reduces it to a much smaller size. The whole problem becomes smaller. And then you can perform the decomposition on the small sketch instead of on the full matrix. And that's standard practice, right? Multiple sketches are then taken, and an empirical certification procedure, it's going to run several random trials. You're going to compute the restriction error on each trial. And if the empirical failure rate, or the fraction of the trials exceeding the error threshold, stays below the target probability, then the method is certified to work at that precision level. But of course, if not, then the algorithm increases the oversampling ratio and the retries. And generally, this provides a probabilistic guarantee on the rendered model's accuracy, but it does that without requiring the full data matrix to be stored or to be decomposed. Now, when the agent has to update its reduced models while preserving the metaplectic structure, here's where Port Hamiltonian preserving projection finds reduced bases such that the projected operator maintains that skew dissipative decomposition. So this uses alternating projections similar to the EDMD approach, but initialized with information from previous model reductions in order to maintain its continuity. And if the time iterative algorithm stagnates, or if it fails to converge, then a robust restart mechanism, it reinitializes with fresh random bases, or it can also fall back to a deterministic truncated SVD approach that's guaranteed to produce a valid reduced model even if the optimization is hard, if the optimization problem is a difficult one. When certain variables equilibrate much faster than others, fast, slow, single perturbation theory applies. Again, fast, slow, singular perturbation theory. So suppose that you have a mechanical system where some degrees of freedom, maybe like springs attached to walls, they oscillate very rapidly and they reach approximate equilibrium almost instantly, right? But there may be other degrees of freedom like heavy masses that change slowly. Here, Tikhonov reduction mathematically eliminates the fast variables and it just replaces them with algebraic constraints that they have to satisfy and evolve only the slow manifold. So the surrogate memory update operates on this reduced slow subsystem, tracking long-term patterns and histories without needing to simulate the irrelevant high-frequency oscillations. And then all compositions are designed not separately but together through a unified co-design objective. Rather than first choosing sensors and then designing a controller and then, training a model, doing this all in a linear step-by-step, what we do is the system optimizes all of these simultaneously. The objective function combines the control cost, the identification error in the reduced model, the importance of each state dimension. It combines all of that, and then implicit differentiation techniques will compute how sensitive this objective is to change in the controller gains, in the sensor configurations, and in the model bases. And it does this all without explicitly solving equations at each sensitivity evaluation. This allows a gradient-based optimization that respects all the coupled constraints. Rank selection for all reduced model does not use an arbitrary cutoff, but balances approximation error against computational cost and noise amplification, such that if the data is noisy, then truncating aggressively can amplify the noise in predictions so that the selection trades off these effects. Now, the operational enforcement of AND happens through a series of practical checks during runtime. Port Hamilton compatibility verification confirms that reduced models remain structurally sound. The reduced operator has to, of course, decompose into skew and PSD parts, and the bases must satisfy certain orthogonality and rank conditions. Then the Landauer constraints check that belief updates don't violate energy budgets, because if they would, then the updates are going to be scaled back or they're going to be rejected. And then the metabolic accounting logs. It logs cumulative energy expenditure across all the subsystems, producing a detailed record of how energy was allocated. Okay, so then the system implements a fast feedback loop that responds to budget depletion by increasing the regularization cost for belief updates and also slowing the rate of model retraining, which mimics how a low battery device would reduce its computational load. So the complete AND system, it produces an agent that thinks, it learns, it acts as an integrated physical system. It automatically trades off the precision of its beliefs against the energy cost of maintaining those beliefs. It exploits environmental symmetries to reduce the computational load, and it discovers and uses invariances rather than learning them redundantly over and over again. It also simplifies its internal models when full fidelity proves too expensive. Of course, using model reduction with certified error bounds. And it predicts the future using Koopman operators to identify linear structures in nonlinear dynamics. And it stores memories using bounded Hebbian plasticity. It also allocates its finite energy budget across perception, cognition, and action according to a unified variational principle that maximizes total thermodynamic cost. And all of this emerges not from ad hoc engineering, but from a single principled framework that's grounded in physics. And so this is fundamentally different from how most intelligent systems are built today. Contemporary machine learning typically ignores energy constraints. It typically treats model compression as an afterthought, and it doesn't maintain any thermodynamic consistency at all. And also contemporary control theory. It often assumes unlimited computational resources. So the A&D framework that integrates these concerns from the ground up, producing systems that are inherently energy aware, inherently thermodynamically sound, and they also are optimized for operation under real-world constraints. So by combining agency and intelligence with control, we have emulated bio-cyber agency here.